Okay, let's move on to the parallel lesson and see that we have Kirchhoff's current law. What do we know about Kirchhoff's current law?
All currents entering and exiting a node must have algebraically equal 0.
That's about it. The algebraic sum of the currents entering and leaving a node must equal 0. Must equal 0. Okay? How did we sum that up? There was like basically like a layman's term type of statement that we used. What was that?
Whatever was going in has to come out.
Whatever's going in has to equal what's coming out. Okay, so which direction is current flowing here? Counterclockwise, that's correct. So IT. Where does IT have to go back to? Has to go back to the source, right? Okay. But this node right here, that node right there, IT is going to split, is it not? Okay. So we can look at this and apply Ohm's law, and we can say, well, let's find our total resistance. How do we find resistance in parallel? It's the reciprocated sums reciprocated is one method. So we say that RT is equal to 1 over R1, 1 over R1, plus 1 over R2, plus 1 over R3. So that's one method. The other method would be to convert them all to conductances and add them, because conductance is additive in parallel. Another method that we became very familiar with is product over sum. We can take, when we're dealing with only two branches, we have resistances of two parallel branches, we can take their product and divide it by their sum. So in this case, that would be 2K times 2K, there's the product, over the sum. 2K plus 2K. 2 times 2 is 4. K times K, K squared. And then 2K and 2K are both like terms with similar bases, so we can add them. We'll add the coefficients for 4 and carry the K's as K. Now we have 4 divided by 4 is equal to 1. And K squared divided by K is equal to K. And our total resistance for this circuit would be 1K. From there, we can say, all right, well, we've got 1K total resistance. I know that my total current is equal to source voltage divided by total resistance. In other words, 4 volts divided by 1K ohm, which is equal to what? 4 milliamps, yes? Okay, good question.
With those resistance total, you also just take the resistance value and divide by the number of resistors.
I was getting to that next. Okay. The other method, as we're reminded by Sergeant Myers here, would be if we have the same value resistors in a series of branches, parallel branches, we could take one resistive value, as long as they're all the same, and divide by the total number of times it appears. So the resistive value would be 2K, because they're the same, of course, 2K, and divided by the number of times it appears, twice, the 2 is reduced to 1, leaving us with 1K, which is the same answer that we got before. Any questions about that method? But remember, that only applies to the parallel branches that have the same resistance, and all you're doing is creating an equivalent resistive value for those branches. Okay, so at this point, we've got our total current, 4 milliamps, and now we can examine what happens to that current when it hits the node. Well, what do we know about voltage in parallel? It's common, so it's going to be the same voltage for each branch, yes?
Yes.
All right. So, R1 is feeling 4 volts. True story? Good. R2 is feeling 4 volts. Well, can I simply apply Ohm's law to that now and find out the branch currents? Yes, I can. So if I took 4 volts and divided by 2 k ohms of resistance, how much current would that give me? It's going 2 milliamps. So going across R1, we've got 2 milliamps. Now there's another way that we could do that. We could say, well, this has the same resistance, so therefore it's also going to be 2 milliamps. If it happened to be a different resistive value, we could say, okay, I've got 2 branches, one of them is 2 milliamps. I know that current is additive in parallel, so therefore if I took the total current and subtracted the one that I know, I'll be left with the one that I don't know. In this case, 4 milliamps minus 2 milliamps leaves me with 2 milliamps. So the 4 milliamps that was coming into that node, 2 of it went across R1, 2 of it went across R2. Does Kirchhoff's current law hold true? Yes. What I had going in, 4 milliamps, equals what I had coming out, 2 milliamps plus 2 milliamps. And then, of course, these 2 currents come back together at this node here and add up to equal 4 milliamps going back to the source. Any questions on that?